Close your eyes, dear traveler. Tonight, we're going on the longest journey any human could imagine. We're going to leave Earth behind and travel to the very edge of our solar system, to places where sunlight is just a distant glimmer, where worlds of ice float in eternal darkness, and where the solar wind finally meets the vast ocean of interstellar space. Our journey will take us 4 billion miles from home. We'll visit worlds you've heard of, and worlds you've never imagined. We'll see storms larger than Earth itself, geysers erupting from frozen moons, and rings that shimmer like cosmic jewelry. We'll travel so far that when we look back, Earth will be nothing more than a pale blue dot suspended in a sunbeam. But don't worry, you're safe and warm in your bed. This journey exists in your imagination, in the realm of dreams and wonder. So settle in, get comfortable, and let your mind drift through the cosmos as we begin our voyage. Take a deep breath. Feel yourself becoming lighter, as if gravity itself is releasing its gentle hold on you. You're rising now, slowly at first, then faster. Through your ceiling, through the clouds, through the atmosphere. The sky changes from blue to purple to black, and suddenly, you can see the curve of Earth below you. Welcome to space. Chapter 1. Leaving Earth Behind. We begin our journey 300 miles above Earth's surface, at the International Space Station. From here, our planet looks impossibly beautiful. Swirls of white clouds dance across blue oceans. The continents are brown and green patches, threaded with silver rivers that catch the sunlight. At the edge of our world, the atmosphere glows with a thin blue line, fragile and precious. This is home, the only home humanity has ever known. Every person who has ever lived, every story ever told, every dream ever dreamed, happened on that blue marble floating in the darkness. But tonight, we're going to leave it behind and explore the neighborhood. We fire our engines. The acceleration is gentle but persistent. The International Space Station falls away behind us, growing smaller and smaller until it's just a bright point of light against Earth's illuminated face. We're traveling at 10,000 miles per hour now, then 20,000, then faster still. The moon appears ahead of us, rising over Earth's horizon. It's the first milestone in our journey, our closest celestial neighbor, hanging in the darkness like a silver coin. The moon has been humanity's companion since before we were human, cycling through its phases, pulling at our oceans, inspiring our poets and dreamers. As we approach the moon, you can see it's not the smooth, glowing orbit appears from Earth. Its surface is scarred and battered, covered in craters from 4 billion years of impacts. There's no atmosphere here, no weather to erode the scars of ancient collisions. Every meteorite that has struck the moon has left its mark forever. We pass over the Sea of Tranquility, where human beings first set foot on another world in 1969. The footprints Neil Armstrong and Buzz Aldrin left are still there, perfectly preserved in the lunar dust. Without wind or rain to erase them, those footprints might last for millions of years, a testament to the day we became a spacefaring species. The far side of the moon rolls into view, the hemisphere that never faces Earth. It's even more heavily cratered than the near side, and it contains one of the largest impact craters in the solar system, the South Pole-Aitken Basin, a scar nearly 2,000 miles across. We accelerate again, leaving the moon behind. It shrinks in our rear view, its light dimming. Earth and moon together now, a double planet system, slowly receding into the darkness. We're truly leaving home now. The Earth-Moon system becomes smaller. Within hours, it's the size of a coin held at arm's length. Then a button, then a star. But still, it shines with that beautiful blue light, a beacon in the darkness. We're entering deep space now, the vast emptiness between worlds. This is the real solar system, mostly empty space, with tiny islands of matter scattered across incomprehensible distances. The nearest planet to us is Venus, and it's currently 25 million miles away. At our current speed, it would take us months to reach it. But we're going to cheat. This is a journey of imagination, after all. We can bend the rules of physics for one night. We accelerate faster, impossibly fast, until the stars begin to blur and the distances collapse before us. Our first destination approaches. Chapter 2: Venus, the Veiled World. Venus emerges from the darkness like a brilliant pearl. It's the brightest object in Earth's night sky after the moon, and ancient peoples called it the morning star and evening star, not knowing it was a planet. The Romans named it after their goddess of love and beauty, charmed by its brilliant light. But Venus is not a world of love and beauty. It's a world of hell. As we approach, we see that Venus is completely covered in thick, yellowish clouds. Unlike Earth's white water clouds, these are clouds of sulfuric acid, forever hiding the surface from view. The planet rotates so slowly that a day on Venus is longer than its year. And it rotates backward, meaning the sun rises in the west and sets in the east. We descend through the cloud layers. The atmosphere grows thicker around us, pressing in from all sides. The temperature rises rapidly. By the time we're halfway through the clouds, it's hot enough to melt lead. The atmospheric pressure is 90 times greater than Earth's, equivalent to being 3,000 feet underwater. Finally, we break through the cloud base and see the surface of Venus. It glows with a dim, orange light filtered through the thick atmosphere. The landscape is volcanic, covered in lava plains and volcanic domes. There are mountains here too, including Maxwell Montes, which rises higher than Mount Everest. The temperature at the surface is 900 degrees Fahrenheit, hot enough to make the rocks glow faintly. This heat is trapped by a runaway greenhouse effect. Venus's thick atmosphere of carbon dioxide traps the sun's heat so efficiently that the planet became an oven. Scientists believe Venus might once have had oceans, like Earth, but the greenhouse effect boiled them away billions of years ago. We don't linger on Venus. The heat and pressure would crush and melt any spacecraft we could build. We rise back through the acid clouds, back into the relative coolness of space, and Venus recedes behind us, beautiful and deadly in equal measure. A lesson from Venus: atmospheres matter. The difference between a paradise and a hell can be a few degrees of temperature and the composition of the air. Chapter 3: Mercury, the Swift Messenger. We're traveling inward now, toward the sun. The light grows brighter, the heat more intense. We're approaching Mercury, the smallest planet and the closest to the sun. Mercury appears as a gray, cratered world, looking much like our moon. It has no atmosphere to speak of, just a thin wisp of atoms blown off its surface by the solar wind. Without an atmosphere to distribute heat, Mercury experiences the most extreme temperature range of any planet in the solar system. The side facing the sun reaches 800 degrees Fahrenheit, while the side in shadow drops to -290 degrees. The planet is small, only slightly larger than our moon, and it orbits the Sun at tremendous speed, completing one orbit every 88 Earth days. That's why the Romans named it after Mercury, their swift messenger god. As we orbit Mercury, we see its most distinctive feature, the Calorus Basin, a massive impact crater over 900 miles across. The impact that created this basin was so powerful that it sent shock waves through the entire planet. On the exact opposite side of Mercury, the ground was shattered into a chaotic jumble of hills and valleys by those shock waves. Mercury is a world of extremes, blasted by radiation, locked in a gravitational dance with the Sun that keeps the same hemisphere facing our star every 2 orbits. It's a harsh world, but it's our solar system's innermost sentinel, forever standing guard at the gates of the Sun. We can't go much closer to the Sun than this. The heat and radiation would overwhelm even our imaginary spacecraft. So we turn outward again, back toward the outer solar system, back toward the cold and the dark. But first, we have to pass through home territory again. Chapter 4, Earth and Mars, the terrestrial twins. We're approaching Earth again, but from a different angle now. We've traveled millions of miles, and our home planet looks different from this perspective. We can see the whole disk of Earth illuminated by the Sun, like a blue Christmas ornament hanging in space. From this distance, you can see how special Earth is. The blue of the oceans, the white of the clouds, the green and brown of the continents. No other planet in our solar system looks like this. Earth is alive in a way that no other world is. We don't stop at Earth this time. We're travelers now, explorers of the solar system. We continue outward, crossing Earth's orbit and heading for the next terrestrial planet, Mars. Mars grows before us, a rusty red disk against the black of space. The red planet has captivated human imagination for centuries. We saw what looked like straight lines on its surface and imagined canals built by Martians. We wrote stories about ancient civilizations and invasions from Mars. We dreamed of the planet as a second home for humanity. As we approach Mars, the first thing you notice is how red it is. The entire planet is covered in iron oxide, rust, which gives it that distinctive color. But it's not uniformly red. There are darker regions and lighter regions, vast plains and towering volcanoes. Mars is about half the size of Earth, with gravity only 1/3 as strong. Its atmosphere is thin, only 1% the pressure of Earth's atmosphere, and it's mostly carbon dioxide. The temperature averages -80 degrees Fahrenheit, though it can get as warm as 70 degrees at the equator during summer, or as cold as -220 degrees at the poles in winter. We orbit Mars, taking in the incredible sights. There's Olympus Mons, the largest volcano in the solar system, rising 16 miles above the surrounding plains. It's 3 times taller than Mount Everest and nearly as wide as Arizona. Despite its immense size, Olympus Mons has very gentle slopes, only about 5 degrees. If you stood on its flank, you wouldn't even be able to see the summit because it would be beyond the horizon. Near Olympus Mons are 3 more massive volcanoes, the Tharsis Mantes. These 4 volcanoes are so massive that their weight has actually deformed the planet, creating a bulge in the Martian crust. On the opposite side of Mars, we see Valles Marineris, a vast system of canyons that dwarfs Earth's Grand Canyon. It's over 2,000 miles long, 4 miles deep, and up to 125 miles wide. If it were on Earth, It would stretch from Los Angeles to New York. This canyon system was probably formed by the same tectonic forces that created the Tharsis bulge, cracking the planet's crust like an overinflated balloon. As we orbit, we see evidence of water everywhere. There are ancient river valleys, dry lake beds, and channels where water once flowed. The polar ice caps contain frozen water and frozen carbon dioxide. Underground, there are vast reservoirs of ice. Mars once had liquid water on its surface. It once had a thicker atmosphere. It might once have been a warm, wet world where life could have emerged. But something happened. Mars lost its magnetic field, and without that protection, the solar wind stripped away much of its atmosphere. The water froze or evaporated into space. The world died, but maybe it's not completely dead. We've found evidence of liquid water flowing occasionally on Mars today. Briny water that can stay liquid in the thin, cold atmosphere. We've found organic molecules in Martian rocks. We've found methane in the atmosphere, which might be produced by geological processes, or might be produced by living organisms. Mars might be sleeping, not dead, and one day, humans might go there and wake it up. We see Mars's two small moons, Phobos and Deimos, captured asteroids that orbit close to the planet. Phobos is slowly spiraling inward and will either crash into Mars or be torn apart by tidal forces in 50 million years. We linger at Mars, dreaming of the day when human footprints will mark its rusty surface, when lights of cities will glow in its thin atmosphere, when it will become humanity's second home. But our journey isn't finished. We have much farther to go. We accelerate outward, leaving Mars behind. Ahead of us lies the asteroid belt, and beyond that, the realm of the giant planets. Chapter 5: The Asteroid Belt, River of Stone. Between Mars and Jupiter lies a vast region of space filled with rocky debris, the asteroid belt. Despite what science fiction movies might show, the asteroid belt isn't a dense field of rocks where you have to dodge and weave. The asteroids are spread across a volume of space so vast that if you were standing on one asteroid, you probably couldn't see any others with your naked eye. Still, there are millions of asteroids here, ranging in size from tiny pebbles to small worlds. The largest is Ceres, nearly 600 miles across, large enough that it's classified as a dwarf planet. Ceres is spherical, with a rocky core and an icy mantle. There might even be a subsurface ocean beneath its frozen crust. We approach Ceres, this lonely dwarf planet orbiting between the terrestrial and giant planets. Its surface is gray and heavily cratered, similar to the Moon. But Ceres has something the Moon doesn't: bright spots. The most famous of these are an Ocata crater, where some kind of bright material, probably salt deposits left behind by evaporating water, creates brilliant white patches that stand out starkly against the dark surface. Ceres might have ice volcanoes, cryovolcanoes that erupt with salty water instead of molten rock. It's a strange, quiet world, too small to be a planet but too large and round to be a simple asteroid. Some scientists think Ceres formed farther out in the solar system, in the realm of ice and snow, and was later scattered inward to its current position. We leave Ceres and drift among the other asteroids. There's Vesta, with its giant impact basin at its south pole and its tall mountain at the center of that basin, twice the height of Mount Everest. There's Psyche, which appears to be the exposed metal core of a planet that never fully formed, or perhaps was shattered by a massive collision early in the solar system's history. Each asteroid is unique, a world unto itself. Some are solid rock, some are loose rubble held together by their own weak gravity. Some are rich in metals, some are made of clay and organic materials left over from the formation of the solar system. The asteroid belt is all that remains of what might have been another planet. When the solar system was young, the material in this region might have coalesced into a fifth terrestrial planet. But Jupiter's immense gravity stirred up the region, preventing the material from settling into a single world. Instead, we have this river of stone, millions of worldlets orbiting between the realms of rock and ice. We drift among the asteroids for a while, contemplating these remnants of creation. Each one has its own story, its own 4 billion-year journey around the sun. Some have been captured as moons by planets. Some have fallen into the sun. Some have struck Earth, bringing both destruction and the building blocks of life. But we can't stay. The giant planets await us, and we've barely begun our journey to the edge of the solar system. We fire our engines and accelerate toward Jupiter, the king of planets. Chapter 6: Jupiter, the king of worlds. Even from millions of miles away, Jupiter dominates the view. It's immense, more than twice as massive as all the other planets in the solar system combined. If Jupiter were hollow, you could fit more than 1,000 Earths inside it. As we approach, the details become visible. Jupiter is a world of clouds and storms, a giant ball of gas with no solid surface. The clouds are arranged in bands parallel to the equator, alternating between light zones and dark belts. These bands are driven by Jupiter's incredibly fast rotation. Despite its immense size, Jupiter completes one rotation in less than 10 hours, making it the fastest spinning planet in the solar system. The most famous feature on Jupiter is the Great Red Spot, a storm larger than Earth that has been raging for at least 400 years, and probably much longer. We can see it now, a vast oval of reddish-orange clouds, rotating counterclockwise in Jupiter's southern hemisphere. The winds at the edge of the Great Red Spot reach speeds of 400 miles per hour. The Great Red Spot is a high-pressure system, an anticyclone, essentially a vast atmospheric mountain of gas that rises 5 miles above the surrounding clouds. The red color might come from complex organic molecules created by sunlight breaking apart the simpler molecules in Jupiter's atmosphere, or it might come from chemicals dredged up from deeper layers. But the Great Red Spot isn't the only storm on Jupiter. There are dozens of smaller storms, some white, some brown, some red. There are storms that last for years and storms that merge with each other. Jupiter's atmosphere is a turbulent, violent place, where winds can reach 600 miles per hour and lightning strikes are more powerful than any on Earth. As we orbit Jupiter, we see that the planet isn't alone. It has at least 9 to 5 known moons, and probably more that we haven't discovered yet. 4 of these moons are large enough to be seen from Earth with a simple telescope. These are the Galilean moons, discovered by Galileo in 1610, Io, Europa, Ganymede, and Callisto. Let's visit each of them. We approach Io first, the innermost of the large moons. Io is the most volcanically active body in the solar system, with hundreds of active volcanoes constantly erupting. As we approach, we can see plumes of sulfur dioxide gas shooting hundreds of miles above the surface. The surface itself is a riot of colors: yellow, orange, red, white, and black, painted by sulfur compounds and silicate rocks. Io is constantly squeezed and stretched by Jupiter's enormous gravity, and this tidal flexing generates tremendous heat in its interior, melting rock and driving the volcanic activity. The surface of Io is so young, constantly renewed by volcanic eruptions, that we can't find a single impact crater. We watch as a volcano called Pele erupts, sending a plume of gas and particles 250 miles into space. The material falls back to the surface in a giant umbrella shape, creating a red ring around the volcano that can be seen from millions of miles away. Io is too hot, too violent, too inhospitable for life as we know it. But it's spectacular, a world of fire and sulfur, forever locked in Jupiter's gravitational embrace. We move on to Europa, the next moon outward. Europa couldn't be more different from Io. Where Io is a world of fire, Europa is a world of ice. Its surface is covered in a smooth sheet of water ice, crisscrossed with dark lines and cracks. Europa is one of the most exciting worlds in the solar system for astrobiologists because beneath that icy crust, there's almost certainly a global ocean of liquid water. The same tidal forces that heat Io also heat Europa, but less intensely. Instead of melting rock, the tidal heating on Europa keeps water liquid beneath the ice. This ocean might be 60 miles deep, containing more water than all of Earth's oceans combined. And where there's liquid water, there might be life. The dark lines on Europa's surface are cracks in the ice where water from below has welled up and frozen. These are places where a future spacecraft might be able to sample the ocean without having to drill through miles of ice. We orbit Europa, studying its smooth, young surface. There are very few craters here, suggesting that the ice is constantly being renewed from below. We see strange features called chaos terrain, where the ice has broken up into blocks and been refrozen in a jumbled pattern. We see ice ridges that might be pressure ridges, like those seen on Earth's polar seas, but hundreds of feet tall. Somewhere down there, beneath the ice, in the dark, pressurized water, life might exist. It might be simple bacteria, feeding on chemicals released by hydrothermal vents on the ocean floor. Or it might be something more complex. We don't know. But Europa is one of the best places in the solar system to search for life beyond Earth. Next, we visit Ganymede, the largest moon in the solar system, even larger than the planet Mercury. Ganymede is big enough to have its own magnetic field, the only moon known to have one. Like Europa, Ganymede probably has a subsurface ocean, buried beneath a crust of ice and rock. Ganymede's surface is divided into two types of terrain: dark, old, heavily cratered regions and bright, younger regions covered in grooves and ridges. The bright terrain was created by tectonic processes in Ganymede's icy crust, perhaps driven by tidal heating or by the freezing of the subsurface ocean, which would cause the crust to expand and crack. We see impact craters with bright rays extending outward, where the impact excavated fresh ice from beneath the surface. We see strange flat-floored craters called patrae, which might be the remnants of cryovolcanic calderas. Ganymede is a complex world, with a history written in its icy surface. It has a metallic core, a rocky mantle, an ocean of liquid water, and an icy crust. It's essentially a planet in its own right, orbiting Jupiter instead of the Sun. Finally, we visit Callisto, the outermost of the Galilean moons. Callisto is the most heavily cratered object in the solar system, its ancient surface a record of 4 billion years of impacts. Unlike the other Galilean moons, Callisto shows little evidence of geological activity. It's a cold, dead world, a time capsule from the early solar system. The most striking feature on Callisto is Valhalla, a vast moldering impact basin over 2,000 miles across. The impact that created Valhalla was so powerful that it sent shock waves through Callisto's icy crust, creating concentric rings like ripples on a pond. Callisto might also have a subsurface ocean, but if it does, it's buried deep beneath the ice and rock, isolated from the surface. This makes Callisto less interesting for astrobiology than Europa or Ganymede, but it's still a fascinating world, a pristine record of the solar system's violent youth. We pull back from the Galilean moons and look at Jupiter again, surrounded by its family of worlds. Jupiter isn't just a planet. It's a miniature solar system unto itself, with dozens of moons, a faint ring system, and an immense magnetosphere that stretches millions of miles into space. Jupiter protects the inner solar system, too. Its enormous gravity acts as a vacuum cleaner, sweeping up comets and asteroids that might otherwise strike Earth. Some scientists think that without Jupiter, Earth might have been hit by many more catastrophic impacts over its history, perhaps preventing complex life from evolving. But we must leave Jupiter behind. We've spent so much time here, exploring its moons and marveling at its storms, that we've almost forgotten we're on a journey to the edge of the solar system. And we're not even halfway there yet. We fire our engines and accelerate outward, toward the next giant planet, Saturn. Chapter 7: Saturn, the Ringed Beauty. As we approach Saturn, the first thing we see are the rings. Even from millions of miles away, they're spectacular, a gleaming disk of ice and rock orbiting the planet. Saturn isn't the only planet with rings, but its rings are by far the most impressive. The rings are thin, incredibly thin. They extend nearly 200,000 miles from one side to the other, but they're only about 30 feet thick in most places. If you made a scale model of Saturn's rings the size of a football field, the rings would be thinner than a sheet of paper. The rings are made mostly of water ice, in particles ranging from the size of dust grains to the size of houses. They reflect sunlight brilliantly, which is why they're so visible and beautiful. The rings are divided into several main sections, separated by gaps where the gravitational influence of Saturn's moons has cleared away the ring particles. The main rings, from innermost to outermost, are called D, C, B, A, F, G, and E. The B ring is the brightest and most massive. The A ring has a prominent gap in it called the Cassini division, named after the astronomer who discovered it in 1675. The F ring is strange and narrow, shepherded by two small moons that keep it from spreading out. We fly through the rings, carefully avoiding the larger particles. It's like flying through a snowstorm, with ice particles glittering all around us. Some particles are as clear as glass. Others are dirty, mixed with rocky material. They orbit Saturn at different speeds, the inner particles moving faster than the outer ones, creating waves and patterns in the ring structure. The origin of Saturn's rings is still debated. They might be the remnants of a moon that was shattered by an impact or torn apart by Saturn's gravity. Or they might be leftover material from Saturn's formation that never coalesced into a moon. Recent evidence suggests the rings might be relatively young, perhaps only a few 100 million years old, which means we're lucky to be living at a time when Saturn has such spectacular rings. We emerge from the rings and approach Saturn itself. The planet is similar to Jupiter, a giant ball of gas with no solid surface, but it's less dense. In fact, Saturn is the least dense planet in the solar system. If you could find an ocean big enough, Saturn would float in it. Saturn's atmosphere is calmer than Jupiter's, with fewer large storms, but it's still a turbulent place. There are bands of clouds, similar to Jupiter's, though less colorful. There's a hexagon-shaped jet stream at Saturn's North Pole, a bizarre six-sided feature that has persisted for decades. At the center of the hexagon is a hurricane-like storm with an eye just like storms on Earth. Saturn has at least 146 known moons, ranging from tiny moonlets embedded in the rings to giant Titan, the second largest moon in the solar system. Titan is our next destination. As we approach, we see that Titan is shrouded in a thick, orange atmosphere, even denser than Earth's. Titan is the only moon in the solar system with a substantial atmosphere, and it's mostly nitrogen, just like Earth's atmosphere. We descend through Titan's atmosphere, passing through layers of orange haze created by complex organic molecules called tholins. The haze is so thick that the surface is invisible from space. But as we descend, the haze clears, and we see an alien landscape below. Titan has rivers and lakes and seas, but they're not made of water. They're made of liquid methane and ethane, hydrocarbons that are normally gases on Earth but are liquids in Titan's incredibly cold environment. The temperature on Titan's surface is -290 degrees Fahrenheit, cold enough to freeze water as hard as rock. We see Kraken Mare, Titan's largest sea, bigger than the Caspian Sea on Earth. We see rivers flowing into the sea, carved by liquid methane rain. We see coastlines and islands and deltas, all the familiar landforms of Earth but made of exotic materials. The solid ground on Titan is made of water ice, as hard as rock in the cold. There are mountains of ice and hills and plains. There are dunes made of solid organic particles, similar to sand on Earth but made of tholins, covering vast areas of Titan's equatorial regions. Titan might be the most Earth-like world in the solar system, at least in terms of having an active hydrological cycle with evaporation, precipitation, rivers, and seas. But instead of water, Titan's cycle runs on methane. Rain falls from the sky, carves channels in the ice, flows into rivers, and collects in lakes and seas, where it evaporates back into the atmosphere to begin the cycle again. Deep beneath Titan's icy crust, there's probably a subsurface ocean of liquid water, kept warm by tidal heating and the decay of radioactive elements. So Titan has two completely separate environments where life might exist: the methane seas on the surface and the water ocean below. We leave Titan and visit some of Saturn's other interesting moons. There's Enceladus, a small, bright moon covered in fresh ice. As we orbit Enceladus, we see something extraordinary. Geysers erupting from the South Polar region, shooting water vapor and ice particles hundreds of miles into space. These geysers come from a subsurface ocean beneath Enceladus's icy crust, and they contain organic molecules and salts, suggesting that the ocean might be habitable. There's Mimas, which has an enormous impact crater called Herschel that makes it look like the Death Star from Star Wars. The impact that created Herschel almost shattered Mimas completely. There's Iapetus, a strange moon with one hemisphere bright white and the other dark as asphalt. The dark material is probably organic-rich dust swept up by Iapetus as it orbits Saturn. There's Hyperion, an irregularly shaped, sponge-like moon that tumbles chaotically through space. Each of Saturn's moons is unique, a world unto itself. But we've spent enough time at Saturn. We need to continue our journey outward, into the deep cold of the outer solar system. We take one last look at Saturn, at its beautiful rings catching the sunlight, at Titan with its orange haze, at the dozens of icy moons orbiting the planet. Then we turn away and accelerate toward the ice giants. Chapter 8: Uranus, the Tilted World. The journey from Saturn to Uranus is long, over 1 billion miles. The Sun is smaller now, less than 1/9 the size it appears from Earth. The temperature in space here is around -350 degrees Fahrenheit. Uranus finally appears ahead of us, a pale blue-green disk. The color comes from methane in its atmosphere, which absorbs red light and reflects blue and green. Uranus is much smaller than Jupiter or Saturn, but it's still massive by Earth standards, 63 times Earth's volume. The most unusual thing about Uranus is that it's tilted on its side. While most planets spin like tops, with their rotational axes roughly perpendicular to their orbital planes, Uranus rolls along its orbit like a ball. Its rotational axis is tilted 98 degrees, meaning its north pole points almost directly at the Sun for part of its orbit, and then its south pole points at the Sun 42 years later. This extreme tilt gives Uranus the most extreme seasons in the solar system. Each pole experiences 42 years of continuous sunlight followed by 42 years of continuous darkness. The planet takes 84 Earth years to complete one orbit around the Sun. No one knows for certain why Uranus is tilted so dramatically. The most likely explanation is that early in the solar system's history, Uranus was struck by a massive object, perhaps an Earth-sized planet, which knocked it onto its side. Computer simulations suggest this impact might have also created Uranus's rings and moons. Speaking of rings, yes, Uranus has rings too, though they're much fainter than Saturn's. They're narrow and dark, made of dust and small particles, and they weren't discovered until 1977 when astronomers noticed stars briefly blinking out as Uranus passed in front of them. We orbit Uranus, studying its bland, featureless atmosphere. Unlike Jupiter and Saturn, with their colorful bands and dramatic storms, Uranus appears calm and serene. But this apparent calm is deceiving. Uranus has the coldest planetary atmosphere in the solar system, with temperatures dropping to -370 degrees Fahrenheit. Winds can reach speeds of 560 miles per hour. Occasionally, massive storms erupt in Uranus's atmosphere, bright spots that appear and disappear over the course of days or weeks. But most of the time, Uranus looks like a featureless blue-green marble. Uranus has 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope. The 5 largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon. We visit Miranda, the smallest of the large moons. Miranda is one of the strangest-looking objects in the solar system. Its surface is a bizarre patchwork of different terrains. Old, heavily cratered regions next to young, grooved terrain, separated by sharp boundaries. It looks like Miranda was assembled from different pieces that don't quite fit together. The most dramatic feature on Miranda is Verona Rupes, a cliff that rises about 12 miles high. It's the tallest cliff known in the solar system. If you jumped off Verona Rupes, you would fall for about 12 minutes before hitting the ground, due to Miranda's low gravity. Scientists think Miranda might have been shattered by an impact and then reassembled, with the pieces coming back together in a jumbled arrangement. Or perhaps tidal heating from Uranus caused some regions to melt and resurface while others remained frozen and ancient. We visit the other large moons briefly. They're all icy worlds, scarred by impacts and geological activity. But none are as bizarre as Miranda. We pull back from Uranus, this pale, tilted giant rolling through space. It's a cold, distant world, so far from the sun that sunlight takes 2 hours and 40 minutes to reach it. But we're going even farther. Our next destination is Neptune, the last of the giant planets and the final planetary-sized world we'll encounter before reaching the edge of the solar system. Chapter 9: Neptune, the windy blue world. Neptune is even farther from the Sun than Uranus, nearly 3 billion miles from home. The Sun here is tiny, barely larger than a bright star. It takes over 4 hours for sunlight to reach Neptune. As we approach, Neptune appears as a brilliant blue sphere, darker and richer in color than Uranus. Like Uranus, the blue color comes from methane in the atmosphere, but Neptune appears deeper blue because there's less haze in its upper atmosphere. Neptune is slightly smaller than Uranus, but it's more massive, denser, and much more active. While Uranus appeared calm and featureless, Neptune is a world of storms and powerful winds. The winds on Neptune are the fastest in the solar system, reaching speeds of over 1,000 miles per hour. These winds drive massive storm systems across the planet. The most famous was the Great Dark Spot, discovered by Voyager 2 in 1989, a storm similar to Jupiter's Great Red Spot. Though that particular storm has since dissipated, new storms continue to form and disappear on Neptune. We can see bright white clouds of methane ice crystals high in Neptune's atmosphere, casting shadows on the cloud layers below. These clouds are driven by convection currents rising from Neptune's warm interior. Unlike Uranus, which is unusually cold and quiet, Neptune radiates more than twice as much heat as it receives from the Sun. This internal heat drives Neptune's dynamic weather. Neptune has 14 known moons, the largest of which is Triton. Triton is special for several reasons, and it's our next destination. As we approach Triton, the first thing we notice is that it's orbiting Neptune backward, in what's called a retrograde orbit. This tells us that Triton wasn't formed alongside Neptune. Instead, it was captured from the Kuiper Belt, the region of icy bodies beyond Neptune's orbit. Triton is the 7th largest moon in the solar system and one of the coldest objects we've encountered, with surface temperatures of -391 degrees Fahrenheit. Only Pluto is colder. Triton's surface is covered in nitrogen ice, which sublimates in the faint warmth of sunlight, creating a thin atmosphere of nitrogen gas. As we orbit Triton, we see something extraordinary. Geysers erupting from the surface, shooting nitrogen gas and dark organic particles up to 5 miles high. These cryovolcanic geysers are driven by sunlight warming the nitrogen ice beneath the surface until it explosively vaporizes and bursts through. Triton's surface is young and geologically active, with relatively few impact craters. There are vast plains of frozen nitrogen, ridges, and strange features called cantaloupe terrain, where the surface is divided into dimpled cells like the skin of a cantaloupe. This terrain might have been created by convection in Triton's icy crust or by ancient cryovolcanism. Triton is slowly spiraling inward toward Neptune due to tidal forces. In about 3 to 4 billion years, Triton will get so close to Neptune that tidal forces will tear it apart, creating a spectacular ring system around Neptune that might rival or exceed Saturn's rings. We also briefly visit Proteus, Neptune's second-largest moon, an irregular, heavily cratered world that barely avoided being pulled into a spherical shape by its own gravity. Proteus is one of the darkest objects in the solar system, reflecting only about 6% of the light that hits it. We pull back from Neptune, taking in the view of this deep blue world with its captured moon slowly spiraling to its doom. Neptune is the last of the major planets, the final giant world. Beyond Neptune lies a different realm entirely, the realm of ice dwarfs and frozen wanderers. We're entering the Kuiper Belt, and our journey to the edge of the solar system is finally approaching its destination. Chapter 10: The Kuiper Belt, Realm of Ice Dwarfs. Beyond Neptune's orbit, about 30 times farther from the Sun than Earth, begins the Kuiper Belt, a vast region of space containing hundreds of thousands of icy bodies left over from the formation of the solar system. These are the building blocks that never quite assembled into planets, frozen in time for 4.5 billion years. The Kuiper Belt extends from about 30 astronomical units from the Sun to about 50 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So we're talking about a region that begins nearly 3 billion miles from the Sun and extends to over 4.5 billion miles. The objects in the Kuiper Belt are mostly made of frozen methane, ammonia, and water, mixed with rocky material. They range in size from tiny ice chunks to dwarf planets hundreds of miles across. These objects are sometimes called Kuiper Belt objects, or KBOs, or transneptunian objects. The most famous resident of the Kuiper Belt is Pluto, once considered the 9th planet, now classified as a dwarf planet. But Pluto is far from alone out here. It has company: Eris, Makemake, Haumea, and thousands of smaller objects. Let's visit Pluto first. As we approach, the Sun is now just a very bright star, providing only about 1/1600th the light that Earth receives. It's perpetual twilight here, but there's still enough light to see. Pluto emerges from the darkness, and it's more colorful and complex than anyone expected. Instead of a featureless, dead ice ball, Pluto has diverse terrain with mountains, plains, and possibly even cryovolcanoes. The most striking feature is Tombor Regio, a vast heart-shaped plain of nitrogen ice named after Clyde Tombaugh, who discovered Pluto in 1930. The western lobe of the heart, called Sputnik Planitia, is a smooth plain of nitrogen ice that appears to be geologically young, with no impact craters. This suggests that Sputnik Planitia is constantly being renewed by some geological process, perhaps convection in the nitrogen ice or slow-flowing nitrogen glacier. Surrounding Sputnik Planitia are mountains of water ice, some reaching heights of 11,000 feet. Water ice is as hard as rock at these temperatures, and it floats on the denser nitrogen ice, creating these mountains. We see evidence of past cryovolcanism, Wright Mons and Pickard Mons, two large mountains that might be ice volcanoes that once erupted with water, ammonia, or methane instead of molten rock. We see glacier of nitrogen ice flowing from the highlands into Sputnik Planitia. We see ancient impact basins and younger smooth plains. Pluto has a thin atmosphere of nitrogen, methane, and carbon monoxide that extends far into space. The atmosphere is slowly escaping into space, but it's constantly replenished by sublimation from the surface ices. When Pluto is closest to the Sun, the atmosphere expands. When it's farthest from the Sun, Much of the atmosphere freezes and falls back to the surface as snow. Pluto has 5 known moons. The largest is Charon, fully half Pluto's diameter and 1/8 its mass. Pluto and Charon are so close in size that they're sometimes considered a binary system rather than a planet and moon. They're tidally locked to each other, meaning the same sides always face each other as they orbit their common center of mass. Charon has its own fascinating features, including a dark polar cap of reddish material that might be methane from Pluto that has been captured by Charon and then modified by radiation. Charon also has a system of canyons that might have formed as its subsurface ocean froze and expanded, cracking the surface. The 4 smaller moons, Styx, Nix, Kerberos, and Hydra, are irregular chunks of ice probably formed from debris after a massive impact in Pluto's early history. We leave Pluto and visit some of the other dwarf planets in the Kuiper Belt. Eris is slightly smaller than Pluto but more massive. It orbits far beyond Pluto, in a very elliptical orbit that takes it as far as 97 astronomical units from the Sun. Eris is covered in methane ice that has refrozen from its atmosphere during the long winter of its distant aphelion, giving it a bright, reflective surface. Eris has 1 known moon, Dysnomia. Makemake is the 3rd largest known dwarf planet in the Kuiper Belt, about 2/3 the size of Pluto. Its surface is covered with frozen methane, ethane, and nitrogen, and it appears reddish in color. Makemake has at least 1 moon, 2 Malawian quachars, which orbits about 13,000 miles from the dwarf planet. Haumea is one of the strangest objects in the solar system. It's shaped like a flattened ellipsoid, like a rugby ball or an American football, because it spins so fast, completing 1 rotation every 4 hours. This rapid spin has stretched Haumea into its elongated shape. Haumea has 2 moons, Namaka and Hyakka, and a ring system, making it the first known Kuiper Belt object with rings. We drift among the other Kuiper Belt objects: Quaoar, Orcus, Gongong, Sedna. Each one is a frozen world, a time capsule from the early solar system. These objects have changed little since they formed 4.5 billion years ago. Studying them is like reading the history book of our solar system's birth. Some Kuiper Belt objects have highly elliptical orbits that bring them close to the Sun periodically. When this happens, the Sun's heat causes their ices to sublimate, creating a glowing coma and tail. These objects become comets, the beautiful visitors from the outer solar system that have inspired wonder and fear throughout human history. The Kuiper Belt is also the source of most short-period comets, comets that orbit the Sun in less than 200 years. When gravitational interactions with Neptune perturb a Kuiper Belt object's orbit, it might fall inward toward the inner solar system, becoming a comet that we can see from Earth. But we're not done yet. The Kuiper Belt is vast, but it's not the edge of the solar system. Beyond the Kuiper Belt lies an even more distant region, a spherical shell of comets that surrounds the entire solar system. We're going to the Oort cloud. Chapter 11: The Scattered Disk and the Oort Cloud, the Final Frontier. Beyond the main Kuiper Belt, between about 50 and 1,000 astronomical units from the Sun, lies the Scattered Disk, a region of space containing objects with highly elliptical orbits. These objects were probably scattered outward by gravitational interactions with Neptune early in the solar system's history. The most distant known scattered disk object is Farfarout, which has an orbit that takes it from 27 astronomical units at its closest to the Sun to 175 astronomical units at its farthest. It takes Farfarout about 1,000 years to complete one orbit. As we travel outward through the scattered disk, the Sun continues to shrink. It's now just a bright star, providing very little warmth. The temperature in space here is only a few degrees above absolute zero, the coldest possible temperature. The objects out here are widely spaced, lonely worlds drifting in the darkness. We pass Sedna, a reddish object about 600 miles across with one of the most unusual orbits in the solar system. Sedna's orbit takes it from 76 astronomical units at perihelion to 937 astronomical units at aphelion, taking 11,000 years to complete one orbit. Scientists don't fully understand how Sedna got its strange orbit. It might have been perturbed by a passing star billions of years ago, or it might be influenced by an as-yet undiscovered massive planet in the outer solar system, sometimes called Planet 9 or Planet X. We're now hundreds of astronomical units from the Sun, farther than any spacecraft humanity has traveled. The stars are clearly visible now without any interference from sunlight. The Milky Way stretches across the sky, a river of stars. We can see other galaxies, faint smudges of light that are actually billions of stars billions of light years away. And ahead of us, still invisible but surrounding us on all sides, is the Oort cloud. The Oort cloud is a theoretical spherical shell of trillions of icy bodies surrounding the solar system. It begins at about 2,000 astronomical units from the Sun and extends to about 100,000 astronomical units, or nearly 2 light-years. At its outer edge, the Oort cloud is nearly halfway to the nearest star. No one has ever directly observed an object in the inner Oort cloud because they're too small and too far away to see, even with our most powerful telescopes. But we know the Oort cloud must exist because of long-period comets that take hundreds or thousands or even millions of years to orbit the Sun. These comets come from all directions, not just from the plane of the solar system, which tells us they must come from a spherical cloud surrounding the Sun. The Oort cloud is thought to contain trillions of objects, most of them small, ranging from 1 to 10 miles across. They're made of water ice, methane, ammonia, and rock, the primordial material left over from the solar system's formation. These objects were probably formed closer to the Sun, in the region where the giant planets formed, and were then ejected to the outer solar system by gravitational interactions with those planets. The Oort cloud objects are so far from the Sun and so weakly bound to it that passing stars can perturb their orbits, occasionally sending one falling inward toward the inner solar system. When this happens, the object becomes a long-period comet, diving past the Sun in a spectacular display before returning to the darkness for thousands or millions of years. We drift through the inner edge of the Oort cloud. The objects here are so far apart that we could travel for years without seeing one. Each object is isolated, floating in the darkness, slowly orbiting the distant Sun. The Sun is just a bright star now. No brighter than Venus appears from Earth. If you didn't know which star was the Sun, you might have trouble picking it out from the background stars. All the planets, all the moons, all the asteroids and comets we've visited are invisible from here, lost in the glare of the distant Sun. This is the edge of the solar system, the boundary between our Sun's domain and interstellar space. The Sun's gravity extends even farther, perhaps as far as 2 or 3 light-years. But beyond the Oort cloud, the Sun's influence becomes negligible. The space between stars begins to dominate. We're now about 50,000 astronomical units from the Sun, about 1 light-year away. At this distance, it takes light 1 year to travel from the Sun to here. We're standing at the edge of everything we know, looking out into the vast darkness between stars. Chapter 12, the heliopause, where the solar wind ends. Before we venture into true interstellar space, we need to talk about the heliopause, the boundary where the sun's influence finally ends. The sun doesn't just emit light and heat. It also emits a constant stream of charged particles called the solar wind. This wind of protons and electrons flows outward from the sun at about 1 million miles per hour, creating a bubble around the solar system called the heliosphere. The heliosphere protects the inner solar system from galactic cosmic rays, high-energy particles that originate from outside our solar system. Without the heliosphere, Earth would be bombarded by much more cosmic radiation, which could be harmful to life. As the solar wind flows outward, it eventually encounters the interstellar medium, the thin gas that exists between stars. The pressure of the interstellar medium pushes back against the solar wind, and where these two forces balance, we have the heliopause. The heliopause is about 120 astronomical units from the Sun in the direction the solar system is traveling through the galaxy, and extends to about twice that distance in the opposite direction, creating a tail-like structure. So we're still within the heliosphere, even this far from the Sun. Only 5 spacecraft launched from Earth have enough velocity to potentially reach interstellar space. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, and New Horizons. Voyager 1 crossed the heliopause in August 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in November 2018. These spacecraft are still operating, sending back data about the environment beyond the heliopause. They've discovered that the interstellar medium is denser than expected and that the magnetic field orientation changes abruptly at the boundary. We drift toward the heliopause, this invisible boundary in space. There's no wall here, no physical barrier. It's just a gradual transition zone where the solar wind slows down and mingles with the interstellar medium. As we cross the heliopause, we feel the change. The constant buffeting of the solar wind ceases. The environment becomes calmer but also more alien. The sun's protective influence is behind us now. We're in true interstellar space, the space between stars. Chapter 13. Into the Void, Interstellar Space. We're now in interstellar space, the vast emptiness between star systems. The sun is behind us, a bright star among billions of others. From here, we can see the solar system for what it truly is, a tiny island of warmth and light in an ocean of cold darkness. The nearest star to our sun is Proxima Centauri, a small red dwarf star in the Alpha Centauri system. It's 4.24 light-years away, or about 40 trillion kilometers, or 270,000 astronomical units. At the speed we've been traveling, it would take us tens of thousands of years to reach it. But we're not going to Proxima Centauri tonight. We're just going to stand here, at the edge of our solar system, and look back at where we've been. From here, if we look back toward the sun, we can see all the planets in our solar system, though they're invisible individually. They're all compressed into a tiny volume of space around that bright star. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all the moons, all the asteroids, all the comets, everything we've visited tonight, all contained within a sphere less than 1/100th of a light-year across. The solar system is vast by human standards, but by cosmic standards, it's tiny. The distances between stars are so much greater than the distances within a star system that it's hard to comprehend. If the Sun were the size of a grapefruit in Los Angeles, Earth would be a grain of sand about 50 feet away, Jupiter would be a small pea 300 feet away, and Pluto would be another grain of sand a quarter mile away. But the nearest star would be another grapefruit in Dallas, over 1,400 miles away. This is the scale of the universe. Vast beyond imagining, empty beyond comprehension, yet filled with wonders at every scale. We float in the interstellar void, feeling small and insignificant, yet also privileged and special. We've traveled farther than any human has ever gone. We've seen worlds that no eye has directly witnessed. We've stood at the edge of our cosmic home and looked out into the infinite. The galaxy surrounds us, 200 billion stars arranged in a great spiral, slowly rotating around a supermassive black hole at the center. Our Sun is just one of those stars, located in a minor spiral arm about 26,000 light-years from the galactic center. Beyond our galaxy are billions of other galaxies, each containing billions of stars, each star potentially surrounded by planets, each planet potentially harboring its own wonders. The universe is vast beyond all human comprehension, filled with more stars than there are grains of sand on all the beaches on Earth. Yet here we are, conscious beings able to understand and marvel at this cosmic magnificence. We are the universe becoming aware of itself, made of star stuff contemplating the stars. Chapter 14. The Journey Home, Reflections. It's time to go home now. We've been to the edge of the solar system and beyond. We've visited worlds of fire and worlds of ice, giant planets and tiny moons, ancient craters and active volcanoes. We've seen the diversity and wonder of our cosmic neighborhood. But as extraordinary as those distant worlds are, none of them are home. None of them have the blue oceans and green continents of Earth. None of them have the warmth of the sun and the protection of Earth's atmosphere and magnetic field. None of them have life, as far as we know, or at least not life as complex and diverse as Earth's. We turn around and begin the long journey back. The sun grows brighter ahead of us as we accelerate inward. The cold darkness of interstellar space gives way to the familiar environment of our solar system. We pass back through the Oort cloud, through the scattered disk, through the Kuiper belt. We wave goodbye to Pluto and its moons as we pass. We accelerate past Neptune with its backward-orbiting Triton, past Uranus rolling on its side, past Saturn with its magnificent rings. Jupiter appears ahead, the king of planets, with its family of fascinating moons. We pass through the asteroid belt, dodging the rocky remnants of what might have been a planet. Mars grows larger, the red planet that might one day become humanity's second home. And then we see it, Earth, the pale blue dot, our home. From this distance, you can see all of it at once, the whole world in a single view. All the oceans, all the continents, all the clouds. 7 billion people down there, going about their lives, mostly unaware of the cosmic wonders that surround them. As we approach Earth, it grows from a dot to a marble to a sphere filling our field of view. We can see the details now, the blue of the Pacific Ocean, the swirl of a hurricane, the brown of the Sahara Desert, the white of the Antarctic ice. We can see the thin blue line of the atmosphere, so fragile, so precious, protecting all life on Earth. We descend through the atmosphere, feeling the warmth return, hearing the sound of air rushing past. The stars fade as the sky brightens from black to blue. We see the clouds up close, the mountains, the forests, the cities. And then we're back. Back in your room, back in your bed, back in your body. The journey is over, but the memories remain. You've traveled 4 billion miles tonight. You've seen wonders that most people only imagine. You've stood at the edge of the solar system and looked out into infinity. Epilogue, sweet dreams, space traveler. And so our journey ends where it began. Here, on Earth, in your room, in your bed. But you're not quite the same person who started this journey. You've seen things now, experienced things, imagined things that have expanded your mind and your sense of what's possible. You've walked on worlds where the rain is made of methane and the ground is made of ice. You've watched geysers erupt into the vacuum of space. You've seen storms larger than entire planets, raging for centuries. You've stood in the light of distant Neptune, where the sun is just another star. You've reached the very edge of the solar system and peered into the void beyond. These worlds exist. They're real. They're out there right now, orbiting the sun, following the same laws of physics that govern everything in the universe. Jupiter's great red spot is swirling at this very moment. Enceladus's geysers are erupting. Titan's methane rain is falling. Pluto's nitrogen ice is slowly flowing across Sputnik Planitia. All of this is happening, constantly, whether we observe it or not. And one day, perhaps, humans will visit these worlds in person. Not in imagination, but in reality. Humans will walk on Mars, swim in Europa's ocean, sail on Titan's seas, stand at the edge of Verona rupees on Miranda. These things might happen in your lifetime, or in your children's lifetime, or in your grandchildren's lifetime. But they will happen because humans are curious and brave and determined to explore. Maybe you'll be one of those explorers. Maybe you'll be a scientist who studies data from distant worlds. Maybe you'll be an engineer who designs spacecraft. Maybe you'll be a writer or artist who helps others understand and appreciate the wonders of the cosmos. Or maybe you'll simply be someone who looks up at the night sky and feels a sense of connection to the vast universe around you. Whatever you do, remember this journey. Remember that you live on a planet that is special and precious and fragile. Remember that we're all in this together, all inhabitants of the same small world. Remember that the universe is vast and full of wonders, and that we're privileged to be conscious beings able to understand and appreciate it. The stars are waiting for us, dear traveler. The cosmos is vast beyond imagining, but it's not beyond our reach. We've already taken the first steps into space, and will take many more in the years to come. But for now, rest. Close your eyes. Let the memories of this journey drift through your mind as you fall asleep. Dream of distant worlds and alien landscapes. Dream of geysers and glacier, of rings and storms, of moons and planets dancing through the darkness. Dream of the pale blue dot, our home, hanging in a sunbeam at the edge of the cosmic dark. Sleep well, space traveler. The universe will still be there when you wake up, vast and ancient and full of wonders, waiting for us to explore it. Good night.